We're talking about reinforced concrete. I didn't realize I had 2 alarms set. I had one that I'd set up for the previous day while I was at ACI and accidentally set it to continuously go. We could have gone over the second example that I had. In hindsight, I'm glad that we didn't. With the reaction to the first one, I probably would have had a complete mutiny on my hands. So we have a different example that we're going to work on today. I'll give you a homework. Once we step through this example, we'll then talk about the lab that we're going to do on Tuesday. Okay? So before we jump into the example, though, I want you to write down, because I think that this will help you with the homework, kind of the steps to go through and solve these problems. Okay, so remember that what we're doing is we're determining beam dimensions, and amount of reinforcement. Okay, so step 1. What are the 2 items that we were given for the previous problem? Well, we were given a lot of items, but when we think back to the shear and bending moments, what did we have to work with for determining our capacity?
You gave us the width.
We had our dead and live loads, right? Yeah. So we use our loading conditions. To determine M sub U, right?
What does that mean?
Our ultimate moment, right? If we combine the loading factors with our dead load and live load, it tells us that ultimate loading condition that we need to be aware of.
I need to write like in parentheses what these are.
Yeah, right. Me too.
Alternate moment wasn't on the vocab test. I'm doing it.
I can't put everything on the vocabulary test, Rush. Okay. The next step, we use MU to determine MT, right? The moment of our tension arm.
And hey Ben.
Yes, sir.
So the MU, the 1.2 dead load and the 1.6 live,
Yep.
never changes. The 1.2 and the 1.6, it's always going to be
Correct. Yep. Yep. So this is the loading. That's the loading condition equation for flexure.
Okay.
We have to remember that there's also
MU's ultimate, and it's determined by the dead load and the live load.
there's also the 1/2 times the moment of the roof load, but we're just looking at beams, so that goes to 0. Okay. But just be aware that it is there, right? Okay, and we need to remember that the reduction factor for flexure, for tension and compression is 0.9. Okay, and so everything that we have, we're looking at flexure. So we're going to be reducing by 0.9.
And MT is
That's the moment of our tension arm, right? Remember that we're looking at a beam. We have our force T.
okay.
We have our force that's in compression, right? Because they're a distance apart from each other, they're going to tend to cause rotation. Right? When we do analysis of our beam and cross section. And then remember that we have some height for our beam, and how we're calculating things is we're calling this
Little d.
distance little d, right? The distance from the face of the beam to the midpoint of the reinforcing steel. Okay? So once we have MT, then we reference table 13.2. And that gives us our rho values, our A over D value, and our R value. Okay?
sheds on?
It's 402, I think.
13.2, I don't have the page number down, 402?
I think so. No, it,
402?
no, it's 406.
406?
Yeah.
I think 402 is where.
400's the 13.1.
13.1, where you've got your dimensions of your steel. Okay, so next we solve for D and we solve for AS. Right, and remember that the equations the area of the steel equals rho times the width times the depth. Okay? And for your assignments, you're going to need to be determining the depth. So at first glance, you're not able to solve for D, but also remember that M sub T equals RBD squared. Right? So D will equal the square root of M sub T over RB. Okay?
So ultimately, we need that.
Yes. But remember, but you have to remember where it comes from, right?
Okay.
Once you know your D value, now you can determine your total area of steel. And remember, what does A sub S represent?
The total, all three.
Area of steel?
Don't just think of it as just 3 bars though.
Cross-sectional.
It's the cross-sectional area of all the steel that we have reinforcing, right? And as John pointed out on Tuesday, we have to keep in mind, this area of steel is for tensile reinforcing steel only. In the event that we have compressive reinforcement, this does not help us determine this value, okay? It's outside the scope of what we're gonna look at. We're only gonna be looking at the tension face in this class, okay? So once we know our depth and we know our area of steel, what do we want to determine next?
If it fits, you need to know the size of your.
Now we need to know, yep, what, the first thing that we do is what is H, right? The total depth of our beam. And what is the allowable distance for reinforcement? Remember that cover equals 1.5 inches for beams. .75 inches for walls and columns. And what dimension are we assuming for our stirrups? Do you remember? 3/8 of an inch.
Yeah, 3.
Okay.
How did I get all the way up to 7?
We can then use A sub S and the allowable distance that we have. To determine quantity and size of our bar, okay?
Can you draw the stirrup diagram thing you did?
Yep.
Like the cross section view?
Right? And so remember that all these dimensions have to be 1.5 inches to meet the code. Okay? And so also keep in mind when you're working with your width, you have to multiply your cover by 2, you have to multiply your stirrup width by 2, right? To reduce your allowable dimension.
And then we use like a, what was that table? 13.1.
Table 13.1 will have your areas, your diameter for your various bar, okay? That makes it simpler, right? There's only 6 steps.
That's like a page.
Not simple at all.
Write smaller.
All right.
Space. I
can remember that one.
When you're doing your, it's not simple.
Yeah,
Sizing your beams and your separations, and we did the one where there's too much space between them when we did it.
yep.
What is acceptable, what isn't acceptable? For,
That's the hard.
you know, we were saying, if you want the big beam, or the big
Yep.
members that there was 3 inches in between them or something.
Yep,
And now we're considering it unreinforced.
correct.
Are we supposed to make that to be 1.5 inches, or what is your goal? What's your allowable?
So it's going to depend. So remember that you have to go back to the code and see what size aggregate are you using, because you can't have smaller openings than the aggregate that you're using. Typically speaking, the design criteria is separated by either the width of the bar, the diameter of the bar, or 1 inch spacing is what you want to look for. Typically speaking.
Whichever is greater. So
Uh,
if you're using a 3/4 inch bar, you can go to 1 inch spacing,
Yep,
and if you're using a 2 inch bar, you can go to 2 inch spacing.
yep.
And you're giving us the size, or do we just assume our aggregate's 3/8 or?
For the purpose of this, we're not gonna complicate things with size of aggregates of the concrete. And.
But we need to know, hey, that's, or is that why Steve was
So,
saying?
so how
keep it
this,
just-
how this works in the real world is, keep in mind, the spacing is given to the ready mix producer.
Yeah,
And the ready mix producer says, okay, now I have to determine how to make this concrete. Okay?
Calm down.
So, if you go to the ready mix producer and say, Mr. Ready Mix Producer, you've got 3/4 inch openings, he is not going to be able to come back and say, you know what? 3/4 inch aggregate is the only way I'm rolling. They've got to figure out how to make it with 3/8 inch aggregate. Okay?
so I think I'm trying to understand what Steve was saying is, whatever your bar diameter is,
Yep.
should be at least your separation.
Correct.
Okay.
Yep.
Unless you're using a 3/8 bar or whatever.
Right.
Yeah,
Which
yeah,
I-
unless you, yeah, if you're using tiny bar, you probably want to, you want to increase that distance.
Yeah.
We want to increase that distance whenever we can, right, to make it easier for our ready mix producer to make their concrete. But there are times where we're not going to be able to make it easy for our ready mix producer, okay? Do you have a follow-up question, Steve?
I'm trying to remember how you said it. So your spacing be a minimum of 1 inch?
Well,
We would like to, but it may not be the case that we're able to. Okay, so if you need to reduce it, don't reduce it smaller than the bar width. Okay, but yeah, whenever you can, I'd like to see that at 1 inch. Whenever possible. Okay? Does everybody have this information? Should we try another example?
yeah,
Okay?
let's do this.
I feel like we're starting from scratch.
I feel like that every time I start in this class,
But
starting from scratch. Brand new lesson, I don't
Well, after midterm, we did start from scratch, right? We moved into concrete. We were looking specifically at concrete.
More so in, we've already looked extensively at these problems. The second one's gonna be from scratch.
Okay, so we have a beam. Our F prime of C is 3,000 PSI. F sub y is 40 KSI. The moment of our dead load in bending is 35 kip feet. The moment of our live load in bending is 28 kip feet. Our beam width is 15 inches. Okay.
Thanks.
Kip is, yes, kip is 1,000 pounds, short for kilo pound, right?
Understand that by now.
So we need to determine
Still don't think I understand what he just brought up there.
D. And I guess subsequently we also need to determine H, right? Because D isn't much help for us. And then our amount of reinforcing. Okay? So what's step one? What should we do first?
So,
M sub U?
Loading condition
MU.
to determine MU. According to the notes.
You just wrote.
So 1.2. So 1.2 times.
Right? So,
So is 1.2, it don't matter what,
It's a constant.
yeah, it don't matter what, that we're KIP or KSI or PSI, it's just, whatever the MDL is, you just 1.2.
yep. Right, because if we put in 20, that's our live. If we put in 35 kip feet, or we put in 35,000 pound feet, it's still going to just increase it by 20%, right? And that 20% increase will be the same regardless of what you look at.
Okay.
Okay? So what does MU calculate out to be?
86, right?
86.8 kip feet,
Ah, see?
right?
Sure.
Yep. Make sure you're tracking your units. Okay, don't trip yourself up. Okay, what's next?
Use MU to FT.
Determine the moment of our tension arm, right?
Yeah, that one.
So that divided by 0.9.
Yep, so take your ultimate moment arm, divided by 0.9.
$96.4.
96.4. And then remember, here we're in kip feet. Our width is in inches, and we're probably going to be working in inches for our depth. So usually this is a good point to change your units. Okay, so multiply by 12, that moves you into kip inches instead of kip feet.
Where did my name take?
And depending on how you round things, ends up giving you about 1,158 kip inches, right? If you're playing the home version.
So refer to table 13.2.
Table 19.
So what are our values for rho, A over D, and R for concrete with F prime C of 3,000 and steel 40 KSI?
.0437.
0437 for rho, A over D,
.685.
685, yep. And what's your value for R?
1.149.
1.149. Okay, and remember that R is in units of KSI. Rho's a unitless dimension because it's a percentage, right? And A over D is also a unitless dimension. It's inches over inches, okay? So what's the equation for the area of the steel? Do you remember?
The P thing,
Yep. Our percentage of steel times the width and the depth of the beam itself, right? So we're just taking whatever percentage of steel we need, multiplying it by that cross-sectional area of the beam. That tells us what we have for area of our steel. Okay?
so do we have D though?
We don't have D.
We don't know D currently,
We know being.
but
So
we
can
know.
I know that you're probably gonna show the whole thing, but remember when I pointed out, so D equals, MT over RB?
Yep.
Would it be sufficient just to be like, okay, I have those,
Yep.
let's just hack that thing out?
Yeah, absolutely, absolutely, yeah.
I get
If you
you're
want
gonna
to
show
do,
it all.
if you want to do D equals the square root of MT over RB first, by all means.
Okay.
And then go and solve for the area of steel, sure. Yeah, how you set that up in your problem is of less concern to me than that you're doing both of them. Does that make sense?
Where'd you get 15 inches from? Oh,
It was defined as part of the problem statement. Okay. Yeah, and then as Rush said, remember that D equals the square root of M sub T RB. Okay?
Yep.
So it equals the square root of 1158 kip inches divided by 1.149 KSI times 15 inches. Okay?
oh.
So looking at your units, what is this thing going to come out as in dimensions?
Inches, squared.
Kip inches squared. No, I don't know.
KSI or GI.
Kips.
Our kips will cancel, right?
What's that size, square inches?
These inches will cancel, right? This will flip up into the numerator and we're taking the square root of it, so it comes out as inches, right? What are we determining? Dimension D, right? The distance from the top face of the beam to the middle of the steel. How are we going to measure that? We're going to measure that in inches, okay? So our dimensions are good. So we're ready to go, okay? So as long as you're using this and as long as you're aware of what you have, okay? So if you have this in pound inches, what would you have to do to reduce? You have to, this value would have to get multiplied by, or sorry, this would have to get divided by 1,000, right? Okay? So you can crank on that number.
Oh, thank God.
What's that?
I was hoping I did that. It's hard to write that into the calculator when you got 1158 divided by
Sure.
1.41 times 15 and square root of it.
Yep.
I did it.
And so depending on your rounding, it should come out to be, I don't know, 8.17 or 8.22 inches or something like that. 8.2 inches, okay? So now we can plug that back into this value. What does it give us for an area of steel then?
Hold on.
5.4 inches squared.
5.4 inches squared. Good job, Terry.
No problem.
Calculated that by hand, didn't you?
Yeah, I,
5.37.
you know, in my head.
So yeah, I mean, depending on how you've been rounding things, where you're dropping things, but it's about 5.4 square inches. Do you have a question, Chad?
I'm just trying, I can't get 8.2 when I put that in the calculator. I've got two different numbers now.
See what I'm saying?
I got 0.25 once, the other one I got 0.88.
Okay, so
67.1.
Which one are you using?
Got two
This?
bones.
Yeah. If you got 60.
So I did 1158. Well, I found out the bottom one first.
So, show me how you type it in.
No, I've done it 2 different times now.
You're just still not wearing slacks anymore? Since you know you're not going to get hard
You know, so this is 1.15. That would impact you. So yeah, try doing it again.
Yeah, I wrote 1.1.
I did 1.149
Yeah,
times
and
15.
Chad, completely in your defense, that's, standing back by where you are, that's very small.
Where I wrote it up here, I wrote that, but I didn't.
Didn't translate it down. Okay. Crank on it again, tell me what you get.
Dad brunch sweater.
Dad brunch sweater? Okay.
He's got one of these dad
Yeah, it's almost brighter back here than it is up on whiteboard.
What's that?
He said, I call this my dad brunch sweater.
Damn brunch sweater.
You probably got a couple of those.
Oh, absolutely.
There we go.
Nailed it.
Alright,
Good.
so I took 1.149 times 15 and got that solution.
17.23.
Okay, so then I took 1158 divided by 17.23, whatever it was, and then square root that.
That's 8.2. I just wrote down all of
You
those.
should have 8.1. That's
That's
what I thought, but I thought about that word.
I just looked at 8.2 in that.
That's a lot of
Okay, so,
figuring.
everybody good? We're in agreement that D equals 8.2 inches. We're in agreement that our area of steel required is 5.4 square inches. Okay. So now what do we want to do? We know what D is, right? But
So
what do we need to be able to tell
you need H.
our contractor? We need to determine what H is, right?
Yeah.
What are the 4 terms we need? We need D, we need our cover,
D.
right?
Allowable distance.
But you need also, you need allowable distance in stirrup.
And what's the third item? What distance does D represent?
You need the space.
Center of the steel.
Measured to the center of the steel, right? So we need the other half of the steel.
Yeah,
Okay.
that number. Shoot, I forgot.
I was trying to, you guys remember.
And typically speaking, because of the size of steel that we're working with, and we'll get to it in a second here when we look at things and when we calculate our final number, should typically be fine just using 1 inch diameter for your bar, okay? If we end up bumping ourselves up to number 10 steel where we've got that extra 1/4 of an inch of distance, we're probably fudging for that in our depth factor when we're rounding up, okay?
Skip all this and say 1 inch steel.
1 inch steel.
So, so we end up with 8.2 plus 1.5
Times 2.
plus 0.375 plus 1/2. We don't need to multiply by 2 right now, because remember, here we're dealing with the depth, right?
Oh.
So we're only dealing with that one thickness. Once we get to
Like
the
side
width.
view, we're
Yep.
just dealing with side view.
Yep. Right, we're dealing in this dimension
Yeah,
here.
okay,
Next, when we go to this dimension, that's where we'll need to multiply by 2,
okay.
okay? So it ends up being
So how do we know
10.575 inches, right? And in actuality, what's probably happening,
is that because we said the bar diameter is 1 inch?
yeah, right, right. But in actuality, we're probably not making a 10.575 inch beam, right? We're probably making it 10 3/4 or 11 inches, or if we really need to, if we really want to sharpen the pencil and figure it out, we'll maybe check and see, hey, can we reduce this to 10.5 inches? Can we cut down on a little bit of material in this thing and still have it take that capacity? Okay, so that's what the designer's actually going to deal with, is how do we get this dimension to something that's that's easier to construct than trying to tell someone to build something 10.575 inches. Okay?
So you're just rounding it up to 11.
So you just want us to
You're not
use
dividing
11?
anything. You're just
Correct.
rounding it up. Okay.
Thank you, Justin.
Now,
Good
isn't
question.
this-
Just making sure I'm not
Yep.
missing something.
Yep.
The bars, we're talking about the 11 inches? Oh, never mind, we're
Yeah.
talking about beam depth.
This is beam
Or height,
depth.
height.
Yep.
Okay, alright.
Yep. Okay. What do we want to determine next?
Size of each, size of the bar.
Quantity and size of bar.
Quantity and size of bar.
Quantity and size of bar. Okay. I'm probably, let me get out of space here, so.
That's the only thing you can get right today.
That's all the numbers for.
Okay, so the bars I looked at were 6, 7, 8, 9, and 10. Okay, so what do we have for,
So let's go 10.
huh?
Game over.
It's like a lottery.
Well, maybe that works, but if we can get smaller steel in there, wouldn't we want to try and put smaller steel?
Number 8.
Got less material?
I'm putting money on 10.
1-8.
Okay, so what's the diameter of these guys? What's the diameter of number 6 steel?
6-8.
6/8, right?
0.87 or point.
Yeah.
This is like the third class we've had today.
What about number 9 bar?
Inch and a quarter, inch and an eighth.
Yeah, it ends up being a little bit larger than an inch and an eighth.
Oh, you're
Okay.
cheating.
What does the number 10 bar end up being?
1.27.
1.27, right? Okay, and what are our areas?
God damn it.
Hold on. I'm gonna write too fast. For 6.44. 0.60. 0.79.
I think 1.
1.2. It goes 1.27. 1.56. Did we miss something there? 8 should be 1. Or 9 is 1, isn't it? Okay.
Yeah, 9 is 1.
Yeah, so 8 is 0.79.
Yep. Okay,
So 1.27.
so if we need 5.4 square inches, does number 6 bar look like a good choice for us?
No.
Probably not, right? We're gonna need 13 or 14 sticks. Doesn't seem like it'll be pretty good. How many are we gonna need if we tried number 8 bar?
So how are you looking at this real quick?
So just look at, remember that
Divided by the area.
the quantity,
What's the area? So then we'd use number freaking 10 bar.
right, equals our area of steel divided by the area of 1 bar. Okay, so if
So
we
we
took,
would use number 10.
if we took 5.4 divided by that 0.44, we're gonna need probably 12 or 13, right?
You're right.
Okay?
Yeah.
Probably one number 11.
Huh?
10, 4.25.
4.25 on that number 10 bar.
See, we did all that math or nothing.
Probably one number 11.
Okay, so we do
So
4.2.
When it's bars like that, if it's over at all, do you go up?
Always round up with bar.
So it'd be 5.
Yep. Yep. Always round up with bar. Because what would happen if we rounded down?
You're gonna lose
We
strength.
don't have enough strength, right? We don't have enough steel, so we don't have enough tensile reinforcement. So when that thing gets loaded, we're gonna end up cracking the concrete.
So we need number 11 bar.
Well, hold on. So we need 5 bars. Okay, so if we use 1 inch spacing, first of all, how much space do we need just for the bar itself?
Yeah, 1.27.
For 1, how much do we need for 5?
6.35.
6.35 inches. And if we have 5 number 10 bars, we'll put 4 1-inch spaces between them, okay? So,
And we don't have our cover.
we need 10.35 inches of allowable space, right? So now that's what we'll check. After we take off our bar, or sorry, after we take off our cover and our stirrups, how much space do we have left?
So that was 3 and,
12.
so we got like an inch left.
So remember that, oops. We have 15 inches minus 2 times 1.5 inch for cover, minus 2 times 0.375 inches for our stirrups. So our allowable width ends up being 11.25 inches. Okay? So what that means is we'll actually have space to go a little bit more than, it didn't write 1-inch spacing up there. So we can use a little bit more than 1-inch spacing. Okay? And so what happens if you get down here and this doesn't work?
Keep going.
Come back up and reiterate, okay?
I'm not gonna-
Terrible.
It's kind of
Real
weird.
world works. But we have to keep in mind too that this is no longer, we aren't calculating things this way. Because of computers, we don't have to sit with notepad and paper cranking on these numbers all the time. The software will do it for us.
How do I know that's better than using 4 number 11 bars with just under 2-inch spacing, which also works?
That could be too.
I guess
Could be as well.
How do you determine what's-
The thing we have to keep in mind, so if you didn't hear Kurt's question, Kurt has a very good question. Kurt said, hey, I looked at number 11 bar works. Why would I put in 5 of the number 10 bar when I could use 4 of the number 11 bar? Keep in mind, all we've been looking at in this instance is bending, okay? If we were really designing this beam, we'd also have to look at what's going on with its shear, what's going on with any torsion, what are other loading conditions that we need to keep in mind, okay? So, very well could be that that's what we end up working with, so.
And I guess, as far as homework problems, could you, if they both work, could you?
As long as they work,
Okay.
yeah, for the purposes of this course, and that's a good question as well. For the purpose of this course, as long as it works, we'll be happy with it.
So then, like after that, like after you like determine which one works, like
Yep.
I'm talking like real life cases.
Yep.
Then you just like determine, like do a cost analysis of different sizes.
Yeah, exactly.
That, right?
How much per foot are you paying for 11 bar versus how much you're paying for a 10-foot bar, things like that.
So we worked out 5 number 10 bars, what spacing is 10.35. The reason why this works is because our 15 inches minus all that gives us a greater number than the 10, but not too great where we need to relook at.
Right. We're not gonna have large areas of unreinforced concrete. Yep. Also a good question.
So that's the end of that problem?
That's the end of the problem. We're done. Done?
Back it up.
Seem reasonable, seem achievable from a homework standpoint? Seem reasonable, seem achievable?
Let's
Bottom equation down there, where did the 2 come from again? Where you're taking 2 times 15 inches?
Oh, okay. So to here, Justin, when we're looking at the width, we have to keep in mind, right? We have an 1.5 inch cover here. We have an 1.5 inch of cover here, and then we have stirrups here, and we have stirrups here. So we're just saying, yep. So you could write in, 15 inches minus 1.5 minus 0.375 minus 0.375 minus 1.5. Okay, same thing. So it's just combining like terms. Okay. So the homework,
One problem.
it will be 3 problems. Okay, so it'll be, write down now, it'll be 13.3C, 13.3D, and then I'm going to post another problem later today. The other 2 problems on there, they have you actually design the entire dimension of the beam, and it goes into, it's a much more convoluted process, okay? And I want us to keep moving. We got a lot of stuff left that we want to look at this semester. So,
What were those two problems?
13.3C and 13.3D. I'll get them posted for you here this afternoon.
You're making up one of your own.
And then, yeah, I'm just gonna come up with another one. I wrote a quick little spreadsheet that allows me to throw in some numbers and figure out what's going on with it, so.
It's on page
You got it?
412.
Page number?
412.
Yes, give me a second here.
Oh, okay.
They're word problems.
Oh, man, so this is like doing 2 weeks, right?
It'll be due next Thursday.
Okay. That's doable.
You can do it, Rush.
That's doable, I mean, so.
I have faith in you.
You know, surprisingly, that took only like a page, so it's not that bad.
Yeah, the problems are on page 412. Okay.
Yeah.
Oh my god.
I'd start doing it while it's fresh, Rush.
I know, right? I'm gonna hit that on Saturday. I'm like, what the?
Oops, sorry. I can't see that on the computer.
Yeah, it looks last.
Just tell him.
Oh, yeah, I'll post it as well.
I'm just gonna read it.
Anybody need this yet?
No.
Everybody got it?
Why?
I guess I can leave it on there, because I'll actually be on the
There you go.
projector actually for the rest of class.
Got a lot of stuff piling up on your,
So if you got your computer handy, you can pop over to the class site, and you'll see for this week I've got 3 documents on there. The first item will be our lab that we're going to run, and I'll pull everything up here so we can reference, and you'll actually see on mine that I've got 4 items because I have the assignment, which I haven't put together for you yet, but you'll see that later today.
can you see the screen?
On the camera?
What's that? Oh, yeah, no, thank you, Kurt. Yeah, we're gonna have to change that so we can see
Oh, yeah, you're,
the full screen. Yeah, it doesn't go
you're
high enough.
yeah, and you sent to the right pretty hard.
Active follower of the channel, get those notifications when you post.
Yep. No, I appreciate you mentioning that. Oh, goodness.
Like, I follow the page, but I don't get a notification. It wasn't until I went back through and tried to watch one of your videos when I found out there wasn't posted any for like a week. Slacking on your YouTube page. That's not how you make millions, Ben.
No, I
Keep them
suppose
posts
not.
Coming.
Suppose not.
Keep them fresh.
You have to have a section where you say, hey, if you like the video, please subscribe. Follow me
Yeah,
on
hit
Twitter."
that little bell there to keep up with all our notifications about statics.
Yeah, I'm sure the list will become long but distinguished very quickly.
Well,
All right, we'll try that.
you start
Everything's
picking
kind
your page to all your students. Like everybody that goes out and likes my page gets me.
Okay, so because of room organization, this portion of the video, it's gonna be a kilter, so you'll have to, I don't know, you'll have to maybe tilt your head a little bit when you look at it online.
If you go to Canvas, to our class, to,
Sounds like a back.
Oh, yeah, that's.
these are for our labs. We're just gonna go over them. Did you write down the homework?
Let's see.
This is 412.
All these energy drinks.
I know, I've been holding it, but if you miss if you blink too long on one of these, then you're just gone.
Well, yeah, I waited till we were done with explaining at least. I had to
Fire
go
there,
on.
you sure it's not something else?
This might be, yeah. Wait, what do you think I'm drinking? I'm just fucking on.
Okay, so the assignment will get posted for you this afternoon. The first document, if you want to take a look at it, it's a PDF. And so it's going to describe next week's lab. Okay, so next week what we're going to do is we're going to look at, and we've talked about this a little bit, we're going to look at the impact of reinforcing on concrete. Okay, and so in the past, those of you who have done strength testing yet, and those of you who haven't, don't worry, you'll get a chance in when you take materials one this fall, but we look at compressive strength of the concrete. Okay, and compressive strength is certainly a good indicator of the quality of our concrete, but what we've been talking about, what we've been focusing on is the flexural strength. And we have to keep in mind that concrete doesn't do a very good job of giving flexural resistance. Okay, and so what we're going to look at is how does the concrete perform when we provide this tensile reinforcement. Okay? And so what we'll do, and these goofy things came in just this week, we're going to cast beams. I forgot. I typically always have my knife on me, and then I just remembered before I went to the airport on Saturday to take it out, and now I don't remember where I left it at my house, which is going to be great because that means that my children will find it. So hopefully my wife isn't aware of this YouTube channel, so that she sees that later today, yells at me about not knowing where my knife is at home.
If she could sit through all that and find out about
Oh yeah, no,
you got
yeah.
a serious creeping problem.
Yeah, no, she has no desire to listen to me talk about any subject matter for more than 15, 20 seconds at a time anyway. So.
That's how you do it.
Understandable.
Oh, now they're doing us.
Tell me I'm wrong.
Well, I'm not. I mean, I think we've explained how brutal it can be.
So we got these guys, so we're gonna make 6-inch square beams, okay? They're gonna be, I think they end up being 20 inches in length, okay? And
So how do you suspend your reinforcing, your rebar?
so for the reinforcing steel, I'm gonna make some out of plywood.
Oh,
That-
so you
that you
can
put 'em in.
So you, okay.
So I can cut out holes in them and
Yeah.
run them through. So, but yeah, that's a very good question. So for our control mixture and our fiber reinforced, we'll use these molds, and then I also got a couple metal molds, steel molds from Braun. One of them is behind Jay there. So, so we'll put you into 3 groups. One of the groups will cast 3 beams that's just our control mixture. One of the groups will cast beams that have the fiber reinforcing in them, and then one of the groups will cast the beams that we put that will have the steel in them. Now, when you get here on Tuesday, you'll notice that the steel for the reinforcing will be running along one of these faces vertically. Okay? The reason for that is when we test these things, we're actually going to rotate them 90 degrees to test. The idea behind it is if there's any settling of the aggregate as the thing is hardening, if we test in this direction, we'd have a strength gradient. So if we rotate it 90 degrees, that aggregate is all running perpendicular to how we're going to load it. Okay, so it won't have an impact on our strength result. So, that being said, what we should talk through is what we're looking at. So again, we'll have no reinforcement. We'll have a mixture that has polypropylene fibers. Okay, so the fibers that I have currently is a product manufactured by W.R. Grace. They're a chemical admixture producer. Well, I shouldn't say, they're not just a chemical admixture producer. Construction material producer. Well, they're just little 2-inch strands of fiber, okay? So we'll put those in at the rate of 5 pounds per cubic yard.
Are you using the mixer?
What's that?
Are we gonna use the mixer or?
Oh, yeah, we're gonna use the mixer. Yeah, once you guys get through materials 1 where you mix it by hand.
Materials one, huh?
Yeah, this fall you guys will mix by hand, so don't worry.
That we get to step back and.
Get a chance, yeah, exactly. So, so these will represent deep beams, right? So we have 6 inches of depth with 6 inches of width. So our width is fairly similar with our depth. And what we should find is that, at least statistically speaking, we're probably not going to pick up a whole lot from those fibers, okay, in the deep beams. But we'll also cast some forms where we'll do a thinner section, okay, so we'll still do the 6-inch wide, but we'll probably knock it down to about 1 inch deep, maybe 1.5 inches. Depends on what I can find for wire reinforcing. And we'll do the same thing. We'll have our non-reinforced, we'll have fiber reinforcing, and then we'll put in some sort of wire mesh in them as well. Okay, and there we should see an increase in that performance of the fibers themselves. Okay. The things you need to certainly be aware of to review is look through these 3 sections, especially for next Tuesday. That covers how to fabricate the beams themselves. Okay, we're going to make them in 2 lifts. Okay, so you'll fill it about half full, and then you'll rod them. Okay, we've got 5/8 inch rods. The number of times that you rod is going to be 1 rod per 2 square inches of surface area of concrete. Okay, so if you have a 6-inch beam and it's 20 inches long, how many rods is that? 60 rods. Okay.
Are you talking about like the agitating rods, or just, what are you talking about? I'm gonna put 60 rods in it.
No. So you're just going to go around and you're just going to
Okay.
60 times, trying not to hit the bottom like I just did. Okay, so just 60 rods, spread it all over the cross-sectional area. Okay, get all 60 rods around. The purpose behind that is we're trying to knock out any of the air that we entrain by
So it
mixing the
does
thing and shoveling it
It
in.
does do like the agitator hole.
Yeah, it has the same effect as if we were vibrating out in the field. Yep. When you get done rodding, you'll have some flat edge trowels spade all along the edges. Okay, get the material out of there, then take a rubber mallet and hit it around 12 to 15 times. Okay, you can hit it pretty hard, especially on the metal ones. They're gonna be able to take a decent amount of force. Remember that the whole purpose of it is we're knocking out air. Okay, if we entrap air in that thing, we're going to push down the strength. It's not going to be representative of our concrete. Okay, you'll do 2 lifts. Okay, so you'll fill it half full. You'll rod the thing. You'll spade the thing. You'll hammer the thing. Fill it. When you fill it the second time, fill it about 1/8 to 1/4 of an inch overflowed. Okay, the idea is as we consolidate this thing, it's going to lose volume. We want it to be filled when we're done with the consolidation. Okay, so you'll rod again, you'll spade again, you'll mallet again. Okay, we'll finish the surface. You want to try and minimize the amount of screeding that you're doing, and then I'll have some wet burlap and some plastic. So you put wet burlap right on top of the surface, and then we'll cover it with the plastic to keep it from desiccating over the next 2 days. Okay, on Thursday we'll come in, we'll strip the beams, we'll ID them, and then we'll drop them into lime water. And on the following Tuesday, we'll test them. Okay?
Why lime water?
So why we put lime water in is part of the reaction of cement hydrating is the production of sodium hydroxide. If we put it in lime, or if we put it in water that doesn't have lime in it, the water starts consuming that sodium hydroxide rather than the cement, and you get reduced strength. So, yeah, if you're ever submerging concrete test specimens, you always want to make sure that they're in lime water. They're submerged, so that they continue to have access to sodium hydroxide, that the water isn't pulling it out and creating oxygen and hydrogen gas. Okay. At 7 days, we will test. So the things that we will have to measure, we will have to know what will determine before we test is the length of the span between the 2 supports used. I don't have the apparatus yet. It's not going to get here until probably Monday. But we can take a peek here at this is what this goofy thing looks like. And this is actually center point loading. So I don't want to look at center point loading actually. We want to look at third point loading. This is how we're going to be testing. Okay, so The compression machine, well, you're not gonna be able to see the compression machine because of the door, but it'll be set up when you come in a week from Tuesday, but we'll have a support attached to the spherical seat that has 2 reactions that hit in the beam, and it will have supports. And this looks funky because these should be 6 inches apart. They're doing something weird with this test. As well as these should be 6 inches apart, and these should be 6 inches apart. And so the idea is that the distance between these reactions are the same as the distance between those reactions to create true flexural testing of the system. Okay? So that's what the setup will look like. We'll load the thing. This is L. Okay, the distance from this support to this support. It should be 18 inches. It might be 18.05, might be 17.95, but the dang thing's coming out of the box. It better be 18.00 inches, or I'm going to be pretty upset. But, oops, that's not what I want. You will need to determine the maximum load. That will be right off the indicator on the machine. Okay, when the thing fractures, it's going to tell you what the maximum load is. You will also need to measure the the width of the beam and the depth of the beam. And how we will do that, and I don't have any fractured beams here, but when this thing breaks, you'll take a measurement on each edge of the beam and then at the midspan. Okay, so right in the middle. You do that for the width and you'll do it for the depth. Okay?
Are you looking for like where it expanded or something, or?
No, we just test it afterwards.
Okay, just for the width and the depth, why don't you just, when you're done casting, take it right off the head and back down?
That's how the test method was written. I don't remember the reasoning for
Okay.
the reasoning for that was long before I joined the committee. I don't remember what the reasoning was for determining those dimensions after the test. But yeah, it's a good question. I mean, one of the things that should be looked at, and hopefully is what's the effect on the flexural strength of these members when we determine it with the dimensions after testing versus prior to testing, and how does it compare to samples extracted from structures. Hopefully that was what was looked at before the committee made that change. I'll be honest, I've been a member of ASTM for a handful of years now. That's often not how it happens. So.
Does it generally break pretty clean up and down versus
It's typically not going to, you typically probably won't see a fracture like this.
Well, yeah, it's not going to be clean straight up and down.
It's typically going to be an angle, but what we hope to see, if we manufacture these beams properly, if we cure and store them properly, and if we test them properly, they should fail between those supports. Yep. Because think about what's happening. This is pushing up on it, right? So it's not allowing it to move. This is pushing down,
Yeah.
right? So the tensile face, the greatest stress on the tensile face is going to be right down here. Okay? So it should fracture in that middle third
Where
of
do
the
you
beam.
measure, say it's like this, from here or from here, or a midpoint?
Say that again.
So are we measuring from, the end to where?
So you would measure, yeah, so your width would be from this point of the broken face to the back, on the back side.
Oh, okay.
Does that make sense? Yeah, we're not measuring this.
Okay.
Not measuring that. Okay, we're just interested in the width, which is going into and coming out of the frame of the machine, and then the depth, that vertical condition. Okay, and we'll review that when we get them into the machine, too. Yeah, so then in your calculation, your average beam width will be B, but again, remember, it's going to be the average of the 3, just like the depth is going to be the average of the 3. Okay? When we look at this, what's our units of flexural strength? What's our units of P? Our load? Pounds? Could be kips, right? Kips or pounds. What's our units on L? Inches. Okay, so we have pound inches. What's our units on B?